So today, we're going to talk about something from systems theory called discrete mode observability. Now, I know that sounds super complicated, but it's really about solving a puzzle you probably already understand. How do you know what's going on inside a system when you can't actually look inside? Yeah, really, how do you see inside a black box? This is one of the biggest challenges in engineering and technology. It's a classic problem, and it's absolutely everywhere. Okay, to make this all make sense, let's use an analogy. Picture this. Your friend is in the other room, totally hooked on a video game. You can't see the screen at all. The only clues you have are the sounds. The frantic clicking of the controller, the explosions, the music. That's it. So here's the million-dollar question. Just from those sounds, could you figure out what game they're playing? Is it a fast-paced racing game, some kind of retro platformer, maybe a fighting game? Well, your ability to figure that out, that is exactly what we're talking about today. It turns out this whole guess the game challenge actually has a formal name in systems theory. It's called Discrete Mode Observability, or DMO for short. You can think of it as the detective's toolkit for figuring out these hidden systems. So, put simply, DMO is just the ability to figure out a system's internal mode. Like which specific game is running, based only on its external outputs, like those clicks and sounds you're hearing. You're observing the system to figure out its specific or discrete state. See? It's all in the name. Okay, this slide right here? This is basically our Rosetta Stone. It translates all the tech jargon into our simple game analogy. The switching system, well, that's just the game console. The discrete mode is the actual game being played at that moment. The outputs are the sounds, and observability, well, that's just whether or not you can guess the game. Simple as that. So, how do we actually do this? How do we solve the puzzle without just wild guessing? Turns out there's a secret weapon, and it's a really powerful mathematical tool called graph theory. It helps us build a kind of blueprint of the whole system. And here is the really clever part. Instead of trying to analyze every single little click and sound in real time, which would be, incredibly slow and complicated, DMO uses a shortcut. It creates a map of the system's structure, which gives us this deep insight without having to do all that heavy computational lifting. And check out how easy it is to build this map. Seriously. First, every possible game, every mode the system can be in. We just represent it as a dot. Then, if you can switch from one game to another, you just draw a line between those two dots. And boom, that's it. This simple map, this graph, becomes the blueprint for the entire system. It's what lets us make really smart deductions. But, of course, the real world is messy, right? It's never that clean and simple. So what happens when things get noisy and unpredictable? Well, this is where DMO really starts to shine. Let's go right back to our analogy. You're trying to listen in on the game sounds, but what if someone in the next room turns on a TV and it's blasting? All that extra noise is what we'd call an unknown input. It definitely makes things harder, doesn't it? Can you still pick out the game sounds from all that background racket and make the right guess? This is exactly where that blueprint, that graph, becomes so powerful. Even with all that extra noise, the graph helps engineers figure out which outputs, which sounds, are the most unique to each game. It literally shows them the best place to put their ears, or in the real world, their sensors, to tell the game's signal apart from all the background noise. It's absolutely crucial for keeping an eye on things in complex, messy environments. Okay, so guessing games is a fun way to think about it, but this is way more than just a theoretical exercise. Let's talk about why DTMO is such a critical tool for, well, pretty much all the technology that runs our world. This is where the rubber meets the road. I mean, think about it. Is a self-driving car in emergency brake mode, or is it in lane change mode? Is a part of the power grid stable, or is it about to fail? DMO helps us answer these kinds of life-or-death questions with confidence. It lets us monitor these critical systems and, just as importantly, tells us exactly where we need to put our expensive sensors to get the most bang for our buck. This slide really just sums it all up perfectly. It's the before and after. Before DMO, you're just blindly putting sensors everywhere, hoping for the best. Or you're stuck running these slow, really heavy calculations. With DMO, you get smart, targeted sensor placement, you get fast insights from the graph structure, and, most importantly, you get the confidence of knowing what's actually happening inside your most critical systems. So, as we wrap this up, the question here is a big one, and it's getting more urgent every day. As our tech, from AI to self-driving cars, gets more and more complex, how do we make sure these vital systems never become a total black box to us? Well, concepts like discrete mode observability, they aren't just for academics. They are absolutely essential tools for building a safer and more reliable future.